Hello everyone and welcome to Chemistry Unit 9 Lesson 6. So this is our second lesson in week 3, which is our 6th in total. Alright, this is coming to you on Friday, which will be Good Friday when this is released. So I hope you are taking time to remember the suffering and death of Jesus on the cross. I think, this Lent is, from all of us, a very different Lent, but gives us an opportunity in a real way to experience, in a small part, the suffering of Jesus and not just sort of celebrate the redemptive suffering and death of Jesus. So I hope you're taking some time this Lent to reflect on that and look forward to Easter in the next couple of days. Regardless, Chemistry Unit 9 Lesson 6. Remember next week on Wednesday, which will be Easter week, Dowling is allegedly going to do a sort of live online day on Wednesday, so keep looking out for more information on that. That should be coming from Mr. Maindring. You might find it in the announcements on OnCampus. Alright, so today we're going to talk about not molarity, believe it or not, even though that's what we did the last 2 times, and we will talk about molarity more in the future. We're going to talk about polarity, not molarity. We're going to talk about the meaning of like dissolves like in terms of polar and nonpolar substances, and then we're going to list and explain the colligative properties. Yes, that's lots of words real fast. Alright. Remember, these are the concentration formulas. You must not forget them. You must write them down. Good. Alright. Let's talk a little bit about a concept called polarity. You've probably heard of poles or polar things, right? There's the North Pole and the South Pole. Magnets have a positive pole and a negative pole, right? The positive pole of a magnet's attracted to the negative pole of other magnets, but it repels the other positive poles, that sort of thing. That's what we're talking about, but with molecules. So here's what that means. Polar, all right, means electrons are unevenly distributed in a molecule. If a molecule is polar, some atoms are getting more of the shared electrons than others. If a molecule is nonpolar, then the electrons are being freely and evenly shared like good little kindergartners at a daycare. But most and many, and that we're going to talk about today, many molecules are polar, meaning they're typical kindergartners at a daycare where they don't share their electrons very well. They're unevenly distributed. Right? Anything like any ionic compound is polar. All right? Sodium chloride is polar. Chlorine gets most of the electron. All right? Chlorine becomes negative, like a negative part of a magnet, and sodium becomes positive, like the positive part of the magnet, and they get attracted to each other that way. Water is polar. The oxygen and the hydrogens end up with less of the electron, and oxygen ends up with more of the electron, meaning the oxygen becomes like the negative part of a magnet, and the hydrogens become like the positive part of a magnet. And this affects how the molecules interact with other molecules, right? Because they're basically magnets, all right? The negative oxygen in H2O gets attracted to positive stuff, like sodium, which is positive. The positive hydrogens are like positive ends of a magnet that get attracted to negative stuff they see, like chlorines. All right, so that's what it means to be polar. It means the molecule is not sharing its electrons well, and it becomes something like a magnet. All right, part of it becomes positively charged, part of it becomes negatively charged, and the positive charges are attracted to other negative charges, and the negative charges are attracted to other positive charges. Now, why does this matter? Well, as it turns out, polar things will dissolve in polar things. Nonpolar things will dissolve in nonpolar things. For example, oil is nonpolar, water is polar. One is polar, one is nonpolar, so they don't dissolve in each other. You can't mix them. All right? But salt is polar and water is polar, and you can mix them and they'll dissolve. All right? This is a phrase we call like dissolves like. All right? If they're both polar, they'll mix. If they're both nonpolar, they'll mix. If one's polar and the other's not, they usually won't mix, although there are exceptions and there are chemicals that will make them mix, that sort of thing. What you need to understand is polar things dissolve polar things, nonpolar things dissolve nonpolar things. Like dissolves like. All right. Water, because it's polar, is a good solvent for many compounds. It's a good liquid to dissolve things into. All right. Any compound which has oxygens and hydrogens, so any molecule with oxygens and hydrogens, is probably soluble in water because it's probably polar. All right, compounds with mostly carbon and hydrogen, like oil, are probably not soluble in water because they're probably nonpolar. All right, so the main idea here, polar things dissolve polar things, nonpolar things dissolve nonpolar things, water is polar, and so water dissolves polar things, and many things are polar. All right, that's it. That's all about polar and nonpolar. We'll talk about it more in the future, but just keep in mind that some molecules are polar, meaning they don't share electrons well, they become like magnets. Some molecules are nonpolar, and they share electrons well, and they don't become like magnets, and they like to hang out with their own people. They don't like to hang out with the other people. That's how it works. That's the short answer, the simplistic version for today. Second up, colligative properties. All right, I just want to give you some definitions. We're not going to do any math with them today, but I want to get you exposed to them. Just sort of look at them for a first time. So, there are physical properties of solutions, and they are affected by the number of particles, but not the identity of the particles, and these things are called colligative properties. Now, I know you're at home taking very good notes, but when it's bold like this, you should write it down, and write down the definition right. So, the colligative properties are properties of solutions that are affected by the number, but not the type of particles. All right, so if you have more or less, it affects these things. All right, there's vapor pressure, boiling point, so the vapor pressure lowering, the boiling point elevation, the freezing point depression, and osmotic pressure. These are some examples of colligative properties. Let's look at what they are. So, vapor pressure lowering. Here's what it means. The definition of vapor pressure is the pressure exerted in a closed container by liquid particles that escape the liquid surface and enter the gaseous state. As it turns out, when you pour a liquid into a container, it evaporates. Part of the liquid molecules become gas, right? And they exert a pressure in their container, right? If you fill a Tupperware with water, it exerts pressure on the lid, as it turns out, all right? Adding things which do not become vapor, like salt or sugar, lower the vapor pressure. All right, so if you put a bunch of water in a tank, and it's pure water, all right, the pressure will be higher than if you add salt water to a tank. Because as it turns out, when you add stuff to water, when you dissolve stuff in water, the vapor pressure goes down. So first colligative property is vapor pressure lowering. When you add more stuff, the vapor pressure goes down. The next one, boiling point elevation. Now it's in bold, so write down the definition. If you have to pause the video, do that. The temperature difference between a pure solvent's boiling point and the boiling point of a solution is called the boiling point elevation. Basically this, when you add stuff to a solvent, it takes a higher temperature to boil it. And there's an equation for how to calculate it. It's the change in the temperature is the constant of boiling times the molality of the stuff you add. But basically this, pure water, 100 degrees Celsius, 212 Fahrenheit, that's what it boils at. But you add a bunch of salt to that water, the water will get up to like 110 degrees before it boils. All right, which means it will be hotter before it boils. Boiling point elevation. If you add salt to your pasta water that you're going to boil pasta in, the water will be hotter. Because at 100 degrees, the water boils and it turns into gas, and the actual temperature of the water never gets above 100. But if you add salt, it takes like, say, 102, 103 degrees to boil, which means the water will be hotter and cook the pasta slightly faster and tastier. That's the important point. Freezing point depression. When you add solids to a solvent, the freezing point goes down. So, water. Water freezes at 0 Celsius, 32 Fahrenheit. When you add salt to it, it freezes even lower. So if I have a bunch of water, it's going to freeze at 0 Celsius. But if I add a bunch of salt, it's going to freeze at, say, 10, 20, negative 10 or negative 20 Celsius, way lower. All right? When you add stuff to a solvent, it needs a colder temperature to freeze. The freezing point depresses. This is why in the wintertime we add salt to the roads, right? Because if it's negative 3 Celsius outside, it's going to be ice sheets. But if you add salt, you'll lower the freezing point to, say, negative 5 if you add enough salt. And then it will be liquid water instead of ice. All right, freezing point depression. And you can calculate how much solid you need to add to get a certain temperature. And we'll do that math later, but we're not going to do it today. I just want you to know the definition of freezing point depression. You add solids to a solvent, the freezing point goes down. Finally here, osmotic pressure. Osmotic pressure is the amount of additional pressure caused by the water molecules that move into the concentrated solution by osmosis. Meaning, osmosis is water will pass through a semi-permeable membrane. All right. When you add stuff to the water, all right, it will increase the pressure against that membrane. Osmotic pressure, very simple. We're not going to do math with it. Just write down this definition with the bold word, and that will be sufficient. Okay. Those are just some colligative properties to prime you. We're going to talk about them in the next couple weeks. We're going to do some math with them, but I just want you to be exposed to them and know what they mean. All right. So not a whole lot to talk about today. It is Good Friday. Make sure to tune in around 3 o'clock. Dowling will have a Stations of the Cross available for you to watch. And many of your parishes that you go to will also have a Stations of the Cross for you to watch. So, participate in the prayer of the Lenten season as much as you can, even though it's really not ideal. Anyways, your homework, which will be due next week, Wednesday, Thursday, Friday, somewhere in there. The schedule is going to be weird next week. You go to On-Campus Assignments. You'll click here. And it's a discussion homework. All right. It asks, all right, what are the colligative properties? What all have you learned in the last 3 weeks of chemistry? And how are you dealing with the coronavirus quarantine? All right. How are you feeling? What sort of things are you doing to stay, mentally healthy, physically healthy, those sort of things? Share those with your peers. Maybe it'll be a good idea for them. And then this discussion boards gives you an opportunity to comment on other people's responses and check in with them, right? Your friend says they're doing this and that to be healthier in the coronavirus. Well, great. You can respond to that and encourage them or ask them some questions about whatever they're doing, that sort of thing. So it's an easy homework. Should take you about 3 minutes, 5 minutes, that sort of thing. It's worth a couple points. Have a good Triduum, as good as you can. Have a good Easter. I'll see you next week.